All right, so um, this week the case study is for chapter, I want to say 8. Yeah, dealing with cluster analysis. Um, so, and particularly good for market segmentation, which is what the focus of today's uh, case study is on online perfume and cosmetic sales, understanding customer segmentation through cluster analysis. All right, so um, in the folder, the data is actually in week 6 because the one on the data sheet is not the right data for the case study. So I put the correct one here. So if you want to grab and download that and then open up a uh, Google Colab Python environment and we'll get started.
Is this week's back in the book again, or is this out of the book as well?
No, this one's in the book. So this one should
Thank.
go smooth as written. Yeah, okay, so um, okay, I'll read off the beginning of the case study. So the online perfume and cosmetic industry includes companies that sell products such as cosmetic, fragrances, and skincare. Many of these retailers also sell these products in brick and mortar stores. In recent years, purchasing patterns have shifted, however, and many customers regularly purchase these products using an online channel such as Amazon. So when you're thinking of these companies, it's like Estee Lauder and Revlon, I think you'll see in the data, but those makeup companies is what the aim of the case study is. So at the time of this book, which I think was 2021, 2022, the original revenue in the industry exceeded 16.2 billion annually and is expected to grow substantially over the next several years. The tremendous growth in this industry has also been met with heightened competition from bloggers and social media influencers are using their platform to engage large numbers of followers and introduce them to the different products. They often include personal reviews and direct links to products for customers that make purchasing easy by only requiring a couple of clicks. Online customers can explore products, compare prices, and make purchases from the comfort of their own home within minutes. Okay, so pay particular attention to the next line. A chief marketing officer at one of the leading beauty care company wants to better understand customer behavior. The goal is to segment the market to more effectively engage their customers in marketing campaigns. So I would highlight that sentence. The marketing department understands that developing relationships and strong brand loyalty will translate into greater value for both the customers and the company. In the past, marketing has targeted customers who are periodic big spenders, but this thinking is potentially flawed. Focusing on single large purchases rather than on other behavioral variables overlooks the frequency of visits, the recency of purchases, and the overall customer lifetime monetary value. So the company has collected basic behavioral characteristics from online purchases of cosmetics, fragrances, and skincare. So this behavioral purchasing data will be used to develop more successful market segmentation strategies, which is our goal. Okay, so understanding the data set. We have the transactions number, customer ID, how much they bought, how much it was per unit, the revenue, which is just a calculated field, transaction date. So if you're looking for some kind of time series trend analysis, you could look at that. Product description just says what the product is. Okay. Yeah, so I think it's this one. So when you download it, You can see this is what it should look like across the top. Okay, so what we need to do is first upload our data into our Python environment. So typical upload. Sales. Connect to my Google Drive. Drive. Going to copy this path, but we'll do it later. Okay, so after reviewing the data, what questions can you ask to better understand customer sales? So here are some suggestions. How can the data be grouped using the behavioral characteristics of a customer's recency, frequency, and monetary value? That's kind of the basis of what the variables that we're going to create and then put into the cluster. Um, how can the data be prepared for cluster analysis? That one's a bit more obvious and probably isn't as important to write about. What is the correct number of clusters based on the silhouette score? So determining between, I think we get into 3 clusters or 4 clusters, and deciding which one does a better job segmenting. And what are the characteristics of those clusters once we form that analysis? Okay, so we're not going to use Anaconda from the book. That's a different way of installing packages. And they also use Jupyter Lab, which is kind of a pain because you have to install stuff yourself. And with Google Colab, all of the stuff is generally installed. So we can skip ahead to where we start importing our different packages. So as usual, we'll start out with pandas. PD. Oh, and this time I want you guys to save your file and turn it in with your report. So, and then put something with your name and assignment 6, and then it's going to be an IPy notebook. So after you save that, later we can download it, download as IPy notebook, and then upload that with the other report. Let's see. So download original file maybe. Okay, back here. All right, so first, pandas as PD for importing our data in. We're going to use NumPy as MP, and we're going to use, let's see, not that one, from SciPy import stats. Import date time as DT. So that's our typical just data import, data manipulation packages. So next it puts comment in there, the hashtag for the ones that we're going to use for the actual clustering algorithm. And looks like mine auto-populated that set. Then as part of the clustering algorithm, we're going to visualize it towards the end. So there's going to be several visualization packages we're going to need. No, not spell this. Visualization. Okay. Seaborn is one we've used before. Let's see. That's SBN. Plotlib. T. And from MPL. Tool kits. And plot3 access 3D. Okay, then run that and make sure you get a green checkbox saying all of our libraries are good to go. As we work through it, though, it's going to tell us that some of what we're doing is deprecated, I assume, because, like I said, the case study is 3 or 4 years old now. Okay, so next we need to pull the data in so we can start working with it. In this case study, it makes you use it as a data frame, I think. So we're gonna have to modify this a little bit because we have a CSV that we're working with. For data, we want to call it sales equals pd dot data frame, but we want to change this from the book to pd.read underscore CSV, and then we want to make this section between the single quotes, whatever your path is, here. So online sales.csv, copy path, and then paste it in. Let's see. Close this parentheses. And then we'll double check that it imports because we'll get the first 5 rows of data. All right. So now we are going to work on making the values from our data and transferring them into something useful for a clustering algorithm. You also have to adjust for the date of when this data was we were working with. Hide this. The only part that's different from the book is this is a CSV instead of Excel, and this is the path dependent on your where you put it on your. Yeah, the recording will be posted. So to get to them, if you haven't watched any recordings thus far, you go to the 3 dots next to the collaborate and view all recordings. Okay. So first, we're going to tell it basically when the date that we want it to work off of. So present equals dt dot date time 2021 1:30. We're going to adjust the format of the data or the date to make sure that it's readable in Python. Sales, use a square bracket in it for selecting columns, and it should drop down sales transaction date, PD.to date time, sales transaction date. Um, so that looks good. And then we're going to start delineating inside of the data frame that we're working with the three um, attributes of interest for the clustering algorithm: recency, frequency, and monetary value. Try to capture some of that trend. And the best I can do. Eight. And the date. So what's the change in the date? Present. Predefined. Date. Max. Connected. Okay. Transaction number. X. Date max. Just have days here. Let's look out. Check these. Transaction. X revenue. X X dot and extra on here. Okay. All right. Then we're going to rename our columns to what we to the variables that we created. Columns. I think that's right. RFM.rename columns equals transaction date is recency, transaction number is frequency, and revenue is monetary value. And place equals true. That full head here. Okay. Great. Double check whether run. Create another code box. And it says, let's make sure monetary values are defined as an integer with no decimal places. Value equals RFM. Run ahead here. No, we do. This is okay. RFM.head, and then this should give us the manipulated data frame that gives us our frequency, recency, and monetary value based on customer ID. Let me know if you're caught up. Okay. Okay. So the next bit is we want to view our general statistics. So we'll do our summary or descriptive statistics on this data. All right, them.describe. And we rounded two places here. Okay. Let me know if you're not caught up, and I will try to slow down. So we have our I'm just looking at the means, let's say, for recency, frequency, and monetary value. Look at the mean. I think it's in the book. It's 111, almost 112 days. So that works out to slightly more than 3 months, right? Between 3 and 4 months, because four would be 120 days. So that's the average amount of time between or since the last purchase, I would say. But then the frequency looks to be about 63 days. So basically every other month they are making purchases. And the monetary value is 4,047, which seems really high to be spending that much if those were all to work out together every 2 months. Somebody that's four is making a ton in commission. Okay, are you caught up now? Go back and make sure the spacing's correct and the um, spelling and case sensitivity. So further up here, make sure this F is a capital F. For now, Chris, are you caught up? Can you tell me at what point you are? I can hold the screen at that. Revenue, monetary value, down here. Oh, come on. Hmm. I don't know, is there the line above I would check? Make sure you have the comma there and that the spacing lines up. All right. So I pulled the descriptive statistics. The next um, thing we're going to do is the correlation matrix. Don't think I need around. Um, so it says note the correlation between monetary value and frequency is 0.56. Recency and frequency have a correlation of negative 0.23. Finally, monetary value and recency have correlation of negative 0.11. The negative correlations can be explained by how recency is calculated as the number of days since the last visit. The smaller the value, the more recent the visit. Conversely, the higher the number, the older the visit. I would expect some correlation between those uh, values, but monetary value and frequency being so high, I'm not as expected, but none of them are exceptionally high, and we only are working with three variables. Um, so this next bit of code makes it into a heat map, but it's basically displaying the same data. So title correlation RFM data. Okay. So like I said, it's going to give you the same same information as previous. It just puts it on a heat map so you can see that the higher the color, or in this case, the more red, the more correlated it is. But um, nothing seems to be overly correlated. All right, let me know if I can move on. All right, good to go. All right, so the next one's kind of important because we're going to uh, write let's see, the data that we've basically cleaned and transformed back to a CSV file. So a good thing to know in case you need to bring it back in later. It saves you from having to run all the code up to this point. So RFM dot to underscore CSV. RFM dot CSV. And when it runs, it should over here. Yes. All right, so it took a little bit, but if you hit refresh, it'll populate the CSV here um, that you just created. Okay. So now this case study is kind of interesting because you end up writing a lot of your own functions, which I guess at this point in the book, that's a bit more advanced features. So the first one it's going to do is check skew. So for defining your own function, you always start with DEF, then the name that you plan to use as your function. So check skew, and then you put the parameters that it's going to take in. So it's going to take in a data frame and a column. Then we have to tell Python basically what it is we want this function to do. So skew equals stats dot skew. Skew equals stats dot skew df column. So earlier I had misspelled stats. I think I put state. I had an error. I wasted some time troubleshooting. SBN is not defined. If you go back up here, let's make sure import Seaborn as SBN, because it'll auto sometimes to the wrong SNS, I think. All right, so we're writing this check skew function. And it's going to check the skew and then plot. So we have plot dot title distribution should be in single quotes. Distribution of, and then plus column. So it goes and pulls the column. SBN dot dist plot df column. That's correct. Okay, so print. Here we use double quotes because we're going to use a single quote inside. So we have curly brace, apostrophe S, basically. Q, then another curly brace. Dot 2F. Then outside of the quote, we're going to put format skew. All right, so double check that it runs, and in the book it has return over, but when I ran it earlier, it made me keep the return in line with the rest of the function. All right, let me know when you're ready to keep going. Add another. So assuming it has the green checkbox, our function doesn't have any errors. Now we're going to use that function that we just wrote on the different columns. So we're going to plot 3 graphs, one for recency, frequency, and monetary value. Big size equals 9 by 9. Plot dot figure fig size. Okay. So telling it how big we want our figure to be. Then we're going to tell it what we want in the different subplots. So plot plt dot subplot. Oh, let me double check that. So the first one, plt dot subplot 311. So we're telling it where in the plot we want it. We're using a function check skew on our data frame, and we're pulling the column recency. You can go up here and see we define our function check skew, pulls a data frame and a column. So in position 2, same thing, plt.subplot 312, the position, run our function check skew, RFM, frequency. The last one would be for monetary value. RFM, monetary value. Now the next one is important because if we don't put plt.tot tight layout, the figures will actually overlap and you won't be able to read them very well. And return. Well, if we need that return. I don't think we need that return. Okay. All right, so I created the plots. Take a look at them. So examining the data shows that skewness is a concern for frequency and monetary value. As we can visually see in step 20, to correct this, we will take the log of the variables. So we created our data frame and we're checking for basically if the distribution of the data is normal. And since it has skew, we have to transform it to make it more normal so our statistical tests will work. Okay, let me know when you've got this plot set up. Okay, you're good. All right, so I'm gonna put that and I'll put another one. So first we're going to make a copy of our code, I believe. Yeah. And that way we're going to log transform one of them and leave the standard RFM as in its current state. So we're going to call it RFM underscore log to indicate that it's being log transformed. So running that creates a copy of RFM, call it RFM log. So the next thing we need to do is actually transform that data. So df underscore RFM underscore log. Let's see. What the hell? RFM log. So it's in NumPy. And we want to take the log of RFM log. So this will be the transformed version. So just a warning, not an actual error. We'll see how it goes. Worked fine earlier. Okay, so to speed things up, we're going to copy this code up here. And change the data frame that we're pulling in to be the one we just created. So you can copy df underscore RFM log and paste it over the RFM. Let's see. Monetary value. Didn't have this error before, so A copy of it. DFR NP.log. Why that would have been 0. Well, let's come back to that error in a moment. I'm not sure why it's dividing by 0 and not giving us a value, but I don't know. Yeah, because that should have looked more normal after it was log transformed. Okay, I'll come back to that error in a second, but let's see. In the next step, we're going to make sure they're all on the same scale. So we're going to make a scalar equals standard scalar. So scale data equals scalar dot fit transform. Sorry. Scalar, standard scalar. Scalar dot fit df rfm log, and I'll call this df underscore rfm normal, data that's been normalized by doing scalar dot transform of the log transformed. Then df df underscore rfm normal equals pd dot data frame df rfm normal index equals dfrm log dot index columns dfrfm dot log columns. Sorry, this is scary. Let me go back up and check. This function. That was the only thing I can think of. Okay, so I found where I missed the error. We were supposed to drop columns less than. Let's add a new code up here. So after we imported the data, I missed the line about sales equals sales dot drop sales sales dot quantity less than one square bracket dot x. Okay. So we should still have our sales data in here, but unfortunately, I'm going to have to go through and rerun each of the code boxes from here up to make sure that that future code works. These are not as important, but that should be fine. All matches. I need to copy it. Then I need to log transform it. All right, now we get the correct normal looking chart here. And then that should work now. Okay, if you did not see the line that I added after we imported the data, just add in this line and then run all the code after it up until the point that we get the normalized plot. At that point, we normalize the data and create a new data frame. So here is that like I said, you're going to have to run all the boxes up to this Let's see. The My next suggestion would be make sure that you put the online sales data on your drive and then hit refresh. And when you refresh, then run all the code boxes in sequence, and that should double check and clear out the compiler in case there's something that got messed up. There was a type it up. It's df underscore rfm underscore normal, but I want to look at not describe. I'll pull it up, but from the book, there's not much that I think you can say about it. The data looks normally distributed now, but a mean of zero. Basically, it's just saying we've standardized and normalized the data so that we can work with it. But that's all you can pull from this. The next bit of code is pretty long. Basically, it defines out how we're going to find clusters. So I'll try to fit as much of it on the screen as I can, but it's going to be kind of tight. So it's going to be a long function. So we're going to define it. We'll call it optimal underscore k means. We'll take in a data frame, and it will start with 2 clusters and with 11. The goal of determining what is the optimal number of clusters. So we will initialize the variables that are going to go into this function. So the first one is in underscore clue, which is number of clusters. AMSS. WSS. Talk about in a minute. So I'm creating a function, we're initializing the variables that are going to go into that. Then we're going to start a loop. It's a for loop. So for n underscore clusters in range of start to end, which we defined up above, k means equals k means n clusters equals n clusters. We don't need this random state. K means equals k means n underscore clusters equals n underscore clusters. Then I really wish this would stop. Labels equals k-means dot fit underscore predict df. That creates the cluster labels. The next part is our silhouette average and inertia score. Silhouette score. Silhouette average. Pulling from that a round silhouette score. Silhouette average equals round silhouette score. DF labels. Column 3. We also have a random state equals 1. USS score equals round. And means dot inertia underscore comma 2 2. AM S dot append silhouette average WSS dot append WSS score and include dot append in clusters. So that's correct. That adds the scores to the list that we created earlier. Now we want to print the number of clusters. Print number clusters curly braces silhouette or braces. Hold on. And cluster sum of squares. Hyphens in there. Final double quote goes after the curly braces. Then we have dot format in cluster silhouette average and WSS score. Where does it break it? Here. Last bit of this will plot out the number of clusters that it predicts, and we can use that chart to help us determine what is actually the best number of clusters for market segmentation. In underscore clusters equals end -1, then plot dot figure fixed size, I think it's 9. Plot dot subplot would be 211. Plot dot title is within cluster sum of squares SBN dot print plot point plot, sorry, point plot x equals n clue, y equals WSS. That's correct. Generated these. All right. Plot subplot, correct. And plot subplot 212. Plot title silhouette score. SBN point plot n equals clue, n clue like KMSS. Then tight layout. The plot dot show. Okay, let me scroll back. Okay, let me know when you have caught up on the for loop, or if you need me to go up further. This works. Okay, let me add another code box and make sure this is going to generate optimal means normalized data frame RFM. All right, so it creates it. All right, so let me know when you get caught up. Um, when you generate this last bit of code and run it, after you define the function and run it, it'll tell us that somewhere between 3 and 4 clusters is the optimal um, number of segments. Okay, means are here. So I would double check that it's a capital K here. We redefine it as a with a lowercase k here. As long as we use the same throughout, it should work. K, capital K and capital M. So after you run optimal k means, basically this function we just wrote, like I said, you'll get these two graphs. You can see that somewhere in here is where it kind of optimizes the number of segments. Because doing 2 is obviously not going to be very helpful. But it's odd that it kind of drops really fast at 3 and picks up a little more at 4 before dropping down. So that's why we believe that, somewhere between 3 and 4 segments is the best option. So what we need to do is dig a little bit more into 3 and 4 cluster setups. So now we'll apply the k-means cluster with 2 different cluster sizes, 3 and 4, to tell us which one gives us the better customer segments. This is another function. K-means. Normalized RDF cluster. This here again for a second. So um, I'm not going to be able to tell you. We go and we create a list. So you'll just have to identify what I would assume is there's a missing underscore or something when we're talking about score. All right, so we're defining a new function. Def k means normalized df cluster. Okay, clusters underscore number and original underscore df. Then k means equals km, capital K, capital M means in clusters equals clusters number by cluster number, random state underscore state equals 1. K means fit. K means dot fit normalized df. Cluster labels equals K means labels. Do not forget the last of underscore df underscore new equals original. No underscore df dot assign cluster equals cluster labels, and then return df underscore new. Generative AI is a pain. Okay, let me double check. Define k means normalize df in clusters. Normalize df clusters. Original df. K means in clusters equals in clusters. Random state equals 1. K means dot fit. Normalize df cluster labels. K means dot labels. Df underscore new. Original df assign. Cluster equals cluster labels. Return new. Actually run to instantiate that function. And then we're going to write another function that's going to evaluate the mean and count of each of the variables under each of those clusters. df underscore new. Go df dot group by. Df group by cluster. That should be in single quotes. Okay. Square bracket parentheses. Ag. Okay. Recency, mean count. And then do a dot round to 0. And then return df new. Okay, so we have the two functions, and then now we need to run it for if we have 3 or 4 clusters. df underscore rfm underscore k3 equals k means df rfm normal 3 rfm rf underscore values df rfm k3. Okay. So this shows the recency, frequency, and monetary value and observation counts if we use 3 clusters. Note how customers in cluster 1 have a higher monetary value, amount of money customers spent, higher frequency, generally visit the online store more often, and with more recent visits. A lower value refers to more recent visits. Over the time span, 18 months of the data compared to clusters 0 and 2. So those would be the customers in that segment are the ones you're going to want to target with more advertising or trying to get them to buy more products because they are the ones that are most likely to buy more products and spend more money with higher frequency. At least if you use 3 clusters. Hide this. I create another code block. Let's modify this code to be for 4 clusters. So just change all the 3s to 4s. And run that out. And what we will see. So the ones in the first cluster in this one appear to have, well, second cluster in my generation have the highest spend. It's more recent because the number is less, and the mean is higher, so they spend more frequently, more recent money. So if you were trying to target your advertising further, I think using the 4 clusters will, depending on how much the advertising costs, then if you could target a smaller group that is more likely to pay more money by selecting the customers in this particular cluster. Okay. So I have one more function to define to kind of create a data visualization for what's going on in these tables. So you can uh, get a better idea of what it's doing. All right. So everybody caught up to this part. Okay. A3. EF new. So at the end of each of these, we define DF new. So I would go back. Well, in both cases, we're defining DF new here and here. I would check the indentation, and just make sure that each of these functions are both run. So I'm trying to start working on the next section, because we can be finished after we write this last function and do two more plots. Okay, so we're going to create a function called line plot that takes in a normalized df RFM, df underscore RF m underscore k means, df underscore RFM. So we're going to transform the df normal as a data frame and add the cluster column. So normalized df RFM equals pd dot data frame normalized df RFM columns equals the index equals RFM dot index columns equals RFM dot columns. What the heck? Columns. Second line normalized DFRM cluster equals DFRM k means cluster. Okay, melt data into long format. We can graph it. Underscore df melt equals pd dot melt normalized df underscore rfm dot reset index normalized df rfm dot reset index id bars equals customer id comma cluster value bars equals recency frequency monetary value. Move this down. Then we have bar underscore name equals category equals category value name equals value. All right. And after melt it, then I put our plot.x label will be category plot.y label value SBN point plot point plot data equals df underscore melt x equals category y equals value hue equals cluster. Come on. Then should be return. Okay. Line this up. The last block of code is to generate these two figures. Should be plot dot figure fig size equals 9 plot dot subplot 311. Okay, plot dot title equals line plot for of line plot of k means equals 3. Then what we want to do is pull our function line plot df RFM normal df RFM k3 RFM. Okay, then the second plot will be same as this, but with 4. Then plot type layout. So it says, which do you feel provides a better business meaning of customer segmentation? And it says, upon evaluation, it was determined that 4 segments could assist in developing a more targeted marketing strategy. Which I think was easier to see in the table because we could see that we could target the one cluster that was spending significantly more money than the other 3 clusters. All right. Let me know if you're caught up or you need me to go back. If you are caught up, make sure you go into File and we'll save, and then download as .ipynb and attach it to your submission.